quantity of heat. Before we get into the details, let's get the difference between two terms, heat and temperature. These are two terms that most people often think mean the same thing, but they don't. And it's important as a physicist that we have their definitions correct. So, what is the difference? Let's look at these two items on the screen now. On the left is a cup of coffee and on the right is a lit match. It should be rather obvious really that the match is much hotter or at higher temperature than the cup of coffee. But it's not so obvious that the cup of coffee actually contains much more heat. Let's think deeper by looking at the particles inside. In the coffee, there's millions of particles, all moving fairly slowly. But heat is a measure of the total energy in a system. So if we add up all the energy of each particle, we find there's loads of heat energy in there. Now if you look at the match, you see there's only a handful of particles, and although they are zipping around really quickly, because there are a few of them, if we add up the total energy here, we should find out that it's much lower than that in the coffee. Temperature, however, is a measure of the average energy in a system. And as we can see in the match, the particles are moving much faster than in the coffee. So the average energy and hence the temperature is much higher. So heat is the total energy in a system. And because it's energy, it's measured in the same units of energy, joules. Temperature, however, is the average energy in a system, and there's loads of different units for temperature, such as Celsius, Fahrenheit, and Kelvin. So we move to heat capacity. If we took an ordinary paper cup and hit the cup over a flame, it very quickly bursts into flame. But if we take a paper cup and put water into it, it doesn't burst into flame. We can actually boil water in the cup. We say that water has a very high heat capacity compared to the cup. So the water takes away heat from the cup and prevents it from burning. Heat capacity is defined as the amount of heat energy required to raise the temperature of a given mass of material by 1 degree Celsius or 1 Kelvin. Because of low heat capacity, the temperature of the cup rises very quickly and soon reaches the burning temperature. But water with high heat capacity takes away the heat from the flame, and thus the temperature of the cup remains below the burning point. Heat capacity is given by heat energy absorbed over temperature change, that is C is equal to Q over delta T. The SI unit of heat capacity is joules per Kelvin. Note that delta T is equal to T2 minus T1, where T1 and T2 are the initial and final temperatures respectively. Delta T is always an absolute value. Capacity and nature of substance. Let us perform an experiment to show the dependence of heat capacity on the nature of substance. Take two identical beakers. Pour 200 ml of water in one beaker and 200 ml of oil in the other. Record the initial temperature of water and oil. Heat the 200 ml of water using a Bunsen burner. Note the time taken to raise the temperature of the water by 30 degrees Celsius. Now heat the oil on the same flame till its temperature increases by 30 degrees Celsius. Observe that the time taken is different. This means that the amount of heat gained by a substance depends on its nature or chemical composition and also its mass. The quantity of heat Q absorbed or released by an object of mass m is directly proportional to its mass and the change in temperature delta T. So Q is proportional to m and Q is proportional to delta T. Combining the two expressions, Q is proportional to m delta T. Then Q is equal to Cm delta T, where C is a constant of proportionality called the specific heat capacity of the substance. This expression is better written as Q is equal to mc delta T. By definition, specific heat capacity is the quantity of heat required to raise the temperature of 1 kilogram mass of a substance by 1 degree Celsius or 1 Kelvin. It is denoted by a small c. From this definition, specific heat capacity is heat capacity per unit mass. Thus C is equal to C over m. But then C is equal to Q over delta T. Therefore, C is equal to Q over delta T divided by m. That gives us C is equal to Q over m delta T, and hence we get back to the expression Q is equal to mc delta T. The SI unit for specific heat capacity is joules per kilogram per Kelvin. Let's take an example. A piece of copper of mass 60 grams and specific heat capacity of 390 joules per kilogram per Kelvin cools from 90 degrees Celsius to 40 degrees Celsius. Find the quantity of heat given out. In the solution, Q is equal to mc delta T. This is equal to 0.06 times 390 times 50, which gives us 1,170 joules. Another example. Find the final temperature of water if a heater source rated 42 watts heats 50 grams of water from 20 degrees Celsius in 5 minutes. The specific heat capacity of water is 4,200 joules per kilogram per Kelvin. In the solution, the assumption is that no heat is lost. So heat supplied by the heater is equal to the heat gained by the water. This heat is the energy supplied and it's a work done, remember? Given that power is equal to work over time, then work is equal to power times time. So this is equal to 42 times 5 times 60. We convert that 5 minutes into seconds. And this must be equal to mc delta T, the heat energy gained by the water. If we multiply the left-hand side, we get 12,600 is equal to 0.05 kilograms times 4,200 times delta T. To get delta T, we divide both sides by 0.05 times 4,200. If we do that, we get delta T is equal to 60. Delta T is equal to T2 minus T1. 60 is equal to T2 minus 20. T2 is equal to 80 degrees Celsius. Experimental determination of specific heat capacity. Let us perform an experiment to determine the specific heat capacity of a solid. When determining the specific heat capacity of a substance, we employ the law of conservation of energy, or the principle of calorimetry. According to this principle, in a closed system, heat lost by a hot body is equal to the heat gained by a cold body. Determination of specific heat capacity of a solid by the method of mixtures. In this method, a piece of solid is heated to a high temperature and then quickly transferred to a calorimeter containing cold water. The solid loses heat energy, whereas the water gains heat energy. After some time, the solid, the water and the calorimeter attain the same temperature. Let us perform the experiment to observe this. We will need a copper calorimeter, insulation box, a solid whose specific heat capacity is to be determined, a physical balance, a Bunsen burner, beaker, water, and a thermometer. Take the copper calorimeter with a stirrer. Find the mass using a physical balance. Fill 3/4 of the calorimeter with water. Weigh the calorimeter with water. Calculate the mass of the water. Heat the solid whose specific heat capacity is to be determined as shown here. Continue heating until the temperature of the water becomes constant. Place the calorimeter in the insulating box and note the temperature of the water. Transfer the solid into the calorimeter. Stir the content of the calorimeter and note the final temperature. We calculate the specific heat capacity of a solid by using the principle of calorimetry. According to this principle, heat lost by a hot body is equal to the heat gained by a cold body. The heat gained or lost is calculated using the formula Q is equal to mc delta T. Substitute the recorded values in the equation. Change of state. Heating a material usually leads to a rise in temperature. But there are instances where no observable change in temperature occurs when a material is heated or cooled. Take some ice cubes in a beaker. Suspend a thermometer into the ice cubes and note its temperature. The temperature is 0 degrees Celsius. Heat the ice cubes and record the temperature after every minute. Keep stirring the ice-water mixture constantly so that the temperature is uniform throughout. We observe that the thermometer reading remains constant at 0 degrees Celsius even though heat is being constantly supplied. The temperature remains constant till all the ice melts to water at 0 degrees Celsius. Continue heating the water which is at 0 degrees Celsius. We observe that the temperature is increasing. Record the rise in temperature till the water starts to boil. Continue heating. The boiling water is converted to steam. Observe that the thermometer reading remains constant at 100 degrees Celsius, which is the boiling point of water. That is, there is no change in temperature. This shows that temperature remains constant whenever there is a change of state. If you plot a graph of temperature against time, you will obtain such a graph. What happens to the energy supplied? The energy supplied is used to break the intermolecular forces of attraction, and therefore the thermometer does not register a rise in temperature whenever there is a change of state. Since the energy supplied is not recorded in the thermometer, the heat supplied is called latent heat, meaning hidden. The energy absorbed during the process of melting is called the latent heat of fusion and is defined as the heat required to change the state of a material from solid to liquid without temperature change. Energy absorbed during vaporization is called the latent heat of vaporization and is defined as the heat required to change the state of a material from liquid to vapor without a change in temperature. Specific latent heat. Specific latent heat of a material is the quantity of heat required to change a unit mass of the material from either solid to liquid or liquid to vapor without a change in temperature. So we have specific latent heat of fusion and specific latent heat of vaporization. Q is equal to mLF, where LF is the specific latent heat of fusion. Also, Q is equal to mLV, where LV is the specific latent heat of vaporization. Therefore, LF is equal to Q over M, and LV is also equal to Q over M. The SI unit of specific latent heat is joules per kilogram. Determination of specific latent heat of fusion. We will use the method of mixtures. We will need a copper calorimeter, wooden box, ice, a physical balance, beaker and a thermometer. Take the calorimeter and a stirrer and find their mass using the physical balance. Fill 3/4 of the calorimeter with water and weigh them. Calculate the mass of water. Place the calorimeter inside the wooden box and note the temperature of the water. Take some ice cubes and break them into pieces. Now introduce pieces of ice cubes into the water and stir the calorimeter gently till the ice melts. Add a few more pieces of ice. Record the final temperature of the mixture. Now weigh the calorimeter and its contents to find the mass of the ice that has melted. Calculate the specific latent heat of fusion of ice using the principle of calorimetry. According to the principle, heat gained by ice is equal to the heat lost by water and the calorimeter. Heat gained by ice is equal to mL plus mc2 theta 2. Heat lost by the calorimeter and water is equal to mc1 into theta 1 minus theta 2 plus mc2 into theta 1 minus theta 2. Now substitute the recorded values in the equation and calculate the specific latent heat of fusion of ice, which is the only unknown quantity in this equation. Factors affecting melting and boiling. Melting and boiling are affected by pressure and the presence of impurities. Pressure. Radiation, discovered by Michael Faraday, is the melting of ice under pressure and refreezing when the pressure is reduced. We have an ice cube and a fine cotton thread. Take the thread and hold it over the ice cube. Apply pressure on it. After some time, you can pick the ice cube and the thread, and this is because the thread sinks into the ice and the ice gets reformed on the top. This is due to regelation. Regelation is the reason why glacier flows like rivers. The waters at the base melts under pressure, allowing the glacier to slide ahead, and as it slides, the water moves to the side of the glacier where pressure is low and it refreezes. The presence of impurities lower the melting points of substances. Effects of pressure on boiling points. Fill 3/4 of a round bottom flask with water. Arrange the apparatus as shown here. Heat the water in the flask till it starts boiling. Release the steam with the help of the stopcock. Observe the reading of the thermometer. The thermometer shows 100 degrees Celsius. Now trap the steam inside the flask. What happens? We observe that there is an increase in the thermometric reading. This is because the pressure inside the flask increases due to the trapping of the steam. Now remove the burner and set up the apparatus as shown here. Pour cold water on the flask. The steam condenses. We observe that the water is boiling at a temperature below 100 degrees Celsius. This shows that the boiling point of a liquid can be raised by increasing the pressure and reduced by decreasing the pressure. An application of increased boiling point under increased pressure is made use of in a pressure cooker. In a pressure cooker, the steam is trapped inside. This increases the pressure. As a result, boiling point of water increases to about 120 to 125 degrees Celsius. Thus, cooking of foods become easier and quicker in a pressure cooker. Impurities raise the boiling points. Evaporation. Evaporation is the process by which a liquid changes into vapor at a temperature below the boiling point of the liquid. Evaporation results in cooling as the liquid absorbs heat from its surrounding. Let us perform an experiment to show that evaporation results in cooling. Take a wooden block and sprinkle some water over it. Then place a copper calorimeter on top. Pour some ether in the calorimeter and dip a hollow tube into it as shown here. Blow air in the tube so that the ether is converted to its vapor. Remove the calorimeter. We observe that the water below the calorimeter freezes to form ice. This shows that the ether has absorbed heat from water and also from its surrounding, resulting in the decrease in temperature of the surrounding. Many people often confuse evaporation and vaporization. The two words have quite different meanings. Evaporation is the process by which a liquid changes into vapor at a temperature below its boiling point. Vaporization is the process by which a liquid changes into its vapor at its boiling point. Evaporation takes place at all temperatures. The temperature may change during evaporation. Vaporization takes place only at a fixed temperature called the boiling point, and the temperature during vaporization doesn't change. Evaporation is a slow and silent process. Vaporization is a fast and vigorous process. Evaporation takes place only at the surface of the liquid. Vaporization takes place over the entire mass of the liquid. The rate of evaporation depends upon external factors like surface area of the liquid, wind, humidity, and temperature. The rate of vaporization does not depend on external factors. A magical effect of cooling by evaporation is made use of in a refrigerator. The basic principle of refrigeration is simple. Just pass a cold liquid continuously around the object which is to be cooled. This will take heat out from the object. The whole refrigeration technology is after this: how to produce cold liquid continuously. This is what the inside of a refrigerator looks like. At the heart of the system is a simple device called throttling device. Cold liquid is produced with the help of this phenomenon. In this case, a throttling device is a capillary tube. For effective throttling, an inlet refrigerant should be a high-pressure liquid. Throttling device is an obstruction to the flow which causes tremendous pressure drop. Due to drop in pressure, boiling point of refrigerant comes down and it starts evaporating. The heat required for evaporation comes from within the refrigerant, so its temperature drops. The next phase is simple. Just pass this cold liquid over the body where you have to absorb heat. During heat absorption process, the refrigerant further evaporates and transforms into pure vapor. So we have produced the required refrigeration effect. If we can take this low pressure vapor to the start before throttling process, that is high pressure liquid state, we will be able to repeat this process. A compressor is introduced for this purpose. The compressor will raise the pressure back to its initial value. But since it's compressing the gas, along with the pressure, temperature will also rise. It's unavoidable. Now the refrigerant is a high pressure vapor. To convert it into liquid, the heat exchanger is fitted outside the refrigerator, so it will liberate the heat to the surroundings. Vapor will get condensed into liquid and temperature will come down to the normal level. So the refrigerant is back to its initial state again, a high pressure liquid. This cycle is repeated over and over for continuous refrigeration. This cycle is known as vapor compression cycle.
Now, you see, the people of the day were not completely unaware of electricity. Electricity was known in the 1700s in the form of static electricity. Cuneus at Leiden University in Holland had done various experiments and in fact came up with a device known as the Leyden jar, the only device that was known at the time for the storage of electricity. The problem with this is it was static electricity. The experiments are always very brief in nature because of the short duration of the spark. The voltage is always high, so some of the experiments are a little painful, and there's not much else you can do with it. These two Italians, they came along and they found that by the use of certain dissimilar metals and chemicals, you could generate electrical power on demand, at will. This opened up a whole new vista for research within the field of technology and science.